So, very good afternoon and welcome. I welcome you all to the session on Introduction to Cloud Based Geospatial Data Processing. So, in today's session, we will discuss, briefly, we will divide today's session between two parts. In the first part of the session, I will be just giving you to the basics of cloud based geospatial data processing, and the second half of the lecture, we will see a live demonstration like how do we do actually a cloud-based geospatial data processing, cloud-based geospatial data processing online. Right. So actually, basically, we will be discussing about two cloud-based solutions for geospatial data processing. One we will discuss about Google Earth Engine, and the second we will discuss about Microsoft Planetary Computer. So basically, I will be discussing about what is we will just start with because we are discussing about geospatial data processing on the cloud. So we will start our discussion with what is cloud computing. Starting with the cloud computing, then we will briefly cover the basics of remote sensing that anyway you have already been covered in the previous sections. Then we will discuss about various open source cloud computing platforms are like which all cloud computing platforms are available there, that also free of cost and which provide the facility for processing geospatial data as well. Then we will be discussing about two things. One is Google Earth Engine and another is Microsoft Planetary Computer. Then we will discuss about in detail about Google Earth Engine. And second, in the second part of the lecture, I will show you a live demonstration like how to you, because we have discussed in the previous lecture about Python programs. So same Python we will be accessing the Google Earth Engine computing platform using Python APIs. So first of all, what is cloud computing? So cloud computing is the on-demand delivery of IT services or resources over the internet with pay-as-you-go pricing, right? So it's like the delivery of any other service to your home, like water, electricity, mail service, so any kind of service. So instead of uh, buying the whole infrastructure, like instead of buying all the servers, networking equipment, storage devices, and then deploying on your own premises, instead of that, accessing these all computing resources as a service is called cloud computing, right? So instead of buying, owning, and maintaining the physical IT infrastructure, right here you can see that the previous or on-premise deployments, we buy all the infrastructure and then deploy at our premises and then we use. But in case of cloud computing, we will be using all these computational resources as a service and pay as you go pricing, like we pay for whatever we use, right? So instead of buying, owning, and maintaining physical IT infrastructure, we access the technology services, maybe such as computing, power, storage, database, so any kind of IT services on demand as need basis from maybe any cloud service provider. So it offers, because we need not install anything on our system, so it offers us faster innovation, because instead of spending our time on setting on the infrastructure and maintaining the infrastructure, we can focus on the development, right? So it offers a faster innovation, flexible resources, and economies of scale. Actually, it offers these advantages. Then these are the benefits of cloud computing: cost saving, then we get higher speed, then we can deploy the services globally in the minutes, then we get increased productivity because we focus more on solving the problem instead of focusing more on the IT infrastructure deployment and maintenance. Then performance anyways increase, reliability, because if you are going to set up a high availability system at our on premises system, then we the infrastructure become, or the architecture becomes quite complex. We need to buy two things, like for every server we need to buy a redundant and configure them together. Then like if you want to provide high, then we need to set up a disaster recovery site as well. So but in case of if we are going for the cloud services, these all reliability aspect will be taken care by the cloud service provider, so we need not worry about the redundancy and other things. Then it offers security, as the same security service security features which are giving at on-premises deployment. Similar security features are available on the cloud as well. So the cost saving and agility is the are the most compelling reasons people are going for the cloud. So then types of cloud computing, if basically if you see the types of cloud computing, we can divide into three types. One is called public cloud, private cloud, and hybrid cloud. So in case of public clouds are owned and operated by a third party. So some third party service provider is wholly owning and operating those clouds. So anybody can subscribe to those public cloud service provider and use the cloud services. Then second is private cloud. So a private cloud refers to the cloud computing resources used exclusively by a single business or organization. So when the cloud service provider is catering to or catering or deploying all the resources, whatever he is giving for some particular single organization only. So these all so certain resources are exclusively for a single business or organization, then that case is called a private cloud. Then third is hybrid cloud. So hybrid cloud combines both public as well as private cloud. So it allows the amalgamation of the technology that allows data and application to be shared between them, like because in when we are going for hybrid cloud, so some data we need to keep on the public cloud, some we need to keep on the private cloud. So then hybrid cloud offers us the flexibility of moving the data between these two, so that it will be a combination. Some part of our services will be on the services which are unrestricted or that we are offering to the public can be put on the public cloud part, and things which are more restrictive in nature or services which are more restrictive in nature can be put on the private cloud, and can move the data between these two clouds. So that kind of deployment is called hybrid cloud. So basically, if you see the types of cloud computing services, so the types of cloud computing services which are offered by some service provider, basically are divided into three parts. One is called infrastructure as a service. So in case of infrastructure as a service, we are buying all the hardware as service from the service provider, but the management is done by ourselves. We will discuss in the next detail. And when we are going, the second type of cloud computing service is called is platform as service, and third is called software as service. So infrastructure as service is the most basic category of cloud computing services. Entire IT infrastructure can be availed from a cloud service provider. So in case of when we are taking the cloud services as IaaS, so we are buying the entire IT infrastructure from the cloud service provider. Like we are buying server and storage, maybe network, firewall, security, or right. So, but we need to manage them ourselves. The advantages of this are it reduces the capital expenditure and optimizes costs, increases scale and performance of IT workload, increases stability, reliability, and supportability, then improves business continuity and disaster recovery. So in IaaS, we are buying the entire IT infrastructure, but that IT infrastructure will be managed by us only. The cloud service provider will just provide us servers or maybe networking equipments like that virtual networking equipments and other things. Then, but we need to manage all the things ourselves. Then second type of service is called platform as service. So PaaS refers to the cloud computing services that supply an on-demand environment for developing, testing, delivering, and managing a software. So in the case of PaaS, we are getting an entire infrastructure plus the platform or an environment for developing, testing, and delivering and managing the software as well. So we are not in case of IaaS, we are buying the infrastructure and managing it ourselves. We only are installing operating. We only are supposed to install operating system, connect those systems and all. But in case of when we are going for platform as service, so in that case we are buying the entire platform as service. So hardware plus operating system and maybe some associated softwares also. So this is designed to make it easier for developer to create new applications without worrying about managing the infrastructure. So now the burden of setting up and managing the infrastructure has been moved from us to the cloud service provider. But in case of IaaS, we only were supposed to manage and deploy the infrastructure. So the advantages like cuts the coding time, because now we need not worry about the setting up and managing the infrastructure. So the cloud service provider is going to do. We need to just focus on our application development. So plus it adds development capabilities without adding resources. Develop for multiple platforms, because cloud service provider can easily give us the infrastructure or different platforms like maybe Windows, RHEL, whatever operating system is required. So then if you are going to develop your application can be developed for multiple platforms. Then it supports geographically distributed teams because it is available on internet and our team can be geographically dispersed. Then third is called software as service. So SaaS refers to the cloud computing service that delivers on-demand software applications over the internet. Now, entire software application will be delivered over the internet. So in case of PAS, we were getting just a platform and developing our services. But when we are talking about software as service, in that case, entire software is offered as a cloud computing services. So cloud providers host and manage the software application. They only host and manage the software application and underlying infrastructure and handle any maintenance. So like now SaaS contains our IIS plus PaaS plus maybe some addition the software also. So user connects to the application over the internet, maybe with the browser. So like entire software is hosted by some third party service provider. So our subscribers or our users will be accessing those services just by using a maybe a mobile phone or a web browser. So this is about remote sensing. So remote sensing is art and science of obtaining information about an object or phenomena through analysis through analysis of the data that is obtained by a device that is not in contact with the object or phenomena. So that remote sensing like so the data about earth's feature or surface or the data is called geospatial data. So like this is an images, these are some images. An image can be multi-band, single band or triple band. Then we can create an RGB like this. So now we'll discuss about some cloud open cloud computing platforms where these all geospatial data is available. So there are basically we will discuss about two cloud computing platforms. One is Google Earth Engine. Google Earth Engine is a planetary scale platform for Earth science data and analysis. And second, we will be discussing about a Microsoft Planetary Computer. So we can say a planetary that's what they say, a planetary computer for a sustainable future. So what is Google Earth Engine? So Google Earth Engine is a geospatial processing service powered by Google Cloud Platform. So Google offers a cloud platform called GCP. So Google Earth Engine is a geospatial processing service that is hosted on the Google's cloud. So you can say that this Google Earth Engine is a kind of software as a service. Look, like entire software is provided by the Google to us as a service. So Google Earth Engine is a planetary scale platform for Earth science data and analysis. Right. So it combines a multi-petabyte catalog of satellite imagery and geospatial data sets with planetary scale analysis capabilities. So Google Earth Engines is is not just a processing service as well. So actually it is giving us access to the all the multi-petabyte catalog of satellite data. So all open source satellite data from the all maybe NASA, ESA. So whatever data open source geospatial data is available on the Earth. So almost all of the data is available on the Google Earth Engine. So Google Earth Engine is not just giving us the access to the data; it is giving us tools plus computing resources. It is giving data plus the computing resources to analyze that data as well, right? So it provides an interactive platform for geospatial algorithm development at scale. Like if suppose if you have to do the development at global scale. So suppose if you are going to do in on our local system, our system may not be able maybe not be will not be capable to handle that much information or process that much information. So Google Earth Engine provides us an interactive platform for geospatial application development at global scale. So like look, these are the satellites for which the data is available on the Google Earth Engine. So like you can see if you are interested in getting the GPM data, Landsat 8, Sentinel-1, Sentinel-2, any optical, remote SAR, any kind of data. So almost all of the data which is freely available by any of the data provider. So almost all of the data is available on the Google Earth Engine. So this is more about so Google Earth Engine is a planetary scale platform for Earth science and data analysis. So Earth Engine public data set archive. So the Earth Engine public data archive includes more than 40 years of historical imagery and scientific data sets updated and expanded daily. So almost 40 petabytes of data, and the new data is getting added to that daily on the daily basis. So every day a lot of every the satellites are acquiring new and new data, so the all that data is getting added to the Google Earth Engine data catalog. Plus, this is not just data, so it offers us the entire, so with Google Earth Engine the entire Google Cloud computational infrastructure is at our disposal, right? So suppose if you want to process the CC, assume that if you even searching something in a 40 petabyte of data, it's so difficult storing that data, processing that data. So if you are going to do that in our local system, it's nearly impossible. So with the Google Earth Engine, so entire data plus the entire Google's entire computational infrastructure is available at our disposal. So with just few basic commands, we can query the data, analyze, do some processing on that data, and get answer to the questions which we are interested in from that almost more than 40 years of historical data. So Google Earth Engine is, you can say that, is a big data analysis and visualization platform. So it is a inherently parallel system. So like so whatever requests you are making or whatever processing you are doing, so all the requests is subdivided into sub it is divided into subtasks, and those all tasks will be running in parallel. So it's the inherently parallel system. So basically it is designed for scientists, not for software engineers. So the aim of Google Earth Engine was to empower the scientists who do not know how to program. So actually, basically, Google Earth Engine is designed for scientists. So even if you don't have any programming experience, so with learning some few basic fundamentals, you can start using Google Earth Engine. So its goal was to make it easy for non enable non-traditional users. So its objective was to enable non software programmers or even non remote sensing data users to leverage the power of remote sensing data or geospatial data. So this is focused on societies on solving the biggest challenges of society, what our society is facing today, like maybe deforestation, drought, various disasters, diseases, climate change, conflict, global food security, sustainability. So actually you are limited just by your imagination. So everything is available. All almost 40 plus years of data is available at your disposal. You just need to know few, like what you are looking for, and there are different tools like to analyze the data, but you must know like what information you want to extract from the data. So like this you can create some global mosaics quite easily. Like if you have worked before in geospatial data, you, like suppose if I ask you to create a mosaic of Landsat images for your city itself, so that itself takes a lot of time. And now if I say to create a time lapse of that or do some time series analysis on that data, so it takes a lot of time and resources, and sometimes it becomes impossible to process that data on our local system, maybe our local server as well. But with the help of Google Earth Engine, we can do it just by writing few simple commands, or you can say by just a few simple clicks. Like this, you can create a global mosaic. Like this is a Landsat mosaic of the entire world. Then you can create time lapses quite easily. Like here, you can say that how the snow cover is changing over the years. So this way, these time lapses the time lapses you can create maybe for your city, or you maybe for your area of interest. So if you are interested at global scale, even you can with few commands you can do it for the at the global scale as well. Like this here you can say that how the deforestation is taking place, how the river is changing its course, and how here you can see that how the city is expanding, right? So like this type of time series analysis you can do for your area of interest quite easily using Google Earth Engine. Like same animation you can see that how the city is expanding over the time, how deforestation is changing. Now we'll discuss about data catalog, like which all the data is available at Google Earth Engine. So basically Google Earth Engine contains more than 200 public data sets. Plus there are more than these figures may be quite old. So it contains more than 5 million images plus 4,000 new images gets added to it almost every day. So every day more than 4,000 images are getting added to this. So presently the size of the archive is greater than 60 petabytes. So you have 60 petabytes of data available plus tools and resources to process and analyze that data. Now you are just limited by your imagination, like wow, how to extract, like, or what kind of information you want to extract from that data. So the data is available, like if you are interested in optical data, so Landsat, Sentinel, all satellite imageries are available. Modis data, so even daily Modis data is available. Some vector data is contributed by some user groups are also there. Some terrain and land cover data, weather data, climate data, some biophysical, geophysical. So any kind of data, you name it, almost all of the data is available on the Google Earth Engine. So it's the volume of the data is very huge, right? So it's again the 40 plus years of Landsat imagery. So all the images which have been acquired by any of the Landsat series satellite. So all the images of Landsat, all the images which are acquired by any of the Landsat series satellite are available at the Google Earth Engine. So where maybe Landsat 1, Landsat 4, 5, 6, 7, 8, even Landsat line data also is available now. Plus actually Modis. So if you are interested in Modis data for Modis data, so almost daily Modis composites are also available at the Google Earth Engine. Maybe land products, or for the ocean products or cryosphere products. So any kind. So all Modis products also are available on the Google Earth Engine. And if you are a atmospheric scientist interested in doing accessing the atmospheric data, so almost all of the atmospheric data either maybe from the model or from the satellite, almost all is available. ERA 5 data from ESA or whatever. If you are interested in synthetic aperture radar remote sensing, so almost all of the Sentinel-1 data also is available on the Google Earth Engine. So but now Google Earth Engine can just ingest GRDs. So actually if you are interested in working in single look complexes, then actually Google Earth Engine right now cannot ingest complex data. So only GRD data are available. So if you are interested in synthetic aperture radar data, but only GRD data is available at Google Earth Engine. Then this is the how do we do computation on Google Earth Engine. So there are two ways to do. One, you can do on the fly computation, like you can interactively send a command or query to the Google Earth Engine. Google Earth Engine do that computation and returns back with the result interactively. Right? Or you can do the in batch mode as well, like when you want to do large scale parallel processing. So suppose if you want to do a very large scale processing, and you have multiple steps to be done. So that also, so Google Earth Engine supports both on the fly computation. Interactively you will be sending one command to Google Earth Engine and getting back the result, or you can do it in the batch mode as well. So this is the basic request response. So actually it's just working on the client server architecture. So the user using a web browser works on a web browser, and using some basic APIs, it requests the data from the Google Earth Engine, then can apply some algorithmic. So then there are these all geospatial data sets are residing on the Google Cloud platform, and through some basic algorithmic primitives, the data can be served. Actually, with some basic APIs, we can access the data and apply some algorithmic primitives like convol, distance, add, filter. So whatever focal, mean, focal. So whatever algorithmic primitives are there, we can apply to this data and get back the result interactively. So this is the data model of Google Earth Engine. So first, suppose if you are interested in vector data, so all the vector data are represented as a feature, maybe line, point, or polygon, plus a list of properties. And so any vector data or feature is represented as feature, and images or raster data is represented as an image. So image is a stack of georeferenced bands. So each band will have its mask, projection, resolution, plus a list of properties. Right. So feature, so all the vector data is represented as feature, and a raster data is represented as image. So then second thing comes collection. So collection is a bag of elements. Like when we are combining multiple features together, that will be called a feature collection. And when we are combining together a directory of images, that is called an image collection. Like all the images acquired by Sentinel 2 satellite. So are will be called Sentinel 2 image collection. Like and a single image from that is an image. So map, then something is called map. Map is like suppose if you want to apply certain function to the all images in a image collection. So that is called an apply, like compute area of each feature. Like in our feature collection, there will be multiple features, and suppose if you want to calculate area for each of the feature, maybe like suppose if you want to calculate the cloud cover of each image, so then with the map we can apply certain function on the each images. Then there are some operations called aggregation. So aggregations are reducing the images, maybe either spatially or temporary. So like summarizing the images. So like summed area of overall features, or we can create a median pixel composite from this all satellite images, or can train a classifier using these reduce. Then the second relatively new entrant to the uh, geospatial data services is the Microsoft Planetary Computer. So Planetary Computer combines a multi-petabyte catalog of global environment data with global environment plus satellite data with intuitive API. So it is a flexible scientific environment that allows user to answer global questions about their data, like similar results. So Planetary Computer Hub is then Microsoft Planetary Computer offers a Planetary Computer Hub like Google Earth Engine. That is a development environment that makes user data and APIs accessible through familiar open source tools and allows users to easily scale their analysis. Like if you are interested in doing analysis at the global scale, then either you can use Microsoft Planetary Computer or maybe Google Earth Engine. But Microsoft Planetary Computer doesn't is not as versatile as a Google Earth Engine as of now. But slowly it is also adding new and new features to it. Maybe after some time it will be comparable to the Google Earth Engine. So these are the various components of Planetary Computer. It has a data catalog which contains details of all data, and hub is a Planetary Computer hub, or that is the development environment that makes data and APIs accessible through familiar open source tools and technologies. Then applications, like there are a lot of applications which different users had developed using Microsoft Planetary Computer. Plus it offers APIs as well. So the Planetary Computer API makes it's easy for the users to find exactly what data they need, simplifying search and discovery across the data catalog. So it offers APIs for searching, or what you call filtering the entire data catalog. So the planetary, now you can see these are the different data sets which are available on the Microsoft Planetary Computer. The Planetary Computer data catalog includes petabytes of environmental monitoring data, satellite data. So all the data is in consistent analysis ready formats. So even in Google Earth Engine also all the data are directly ingestible. So they are directly in the analysis ready format. So all of these data sets can be accessed via Azure Blob Storage. Actually, in Microsoft Planetary Computer, the data is stored on Azure Blob Storage. So basically, the Planetary Computer uses open source tools and supports all the open source standards. Incredible ecosystem of tool being developed in the open by much broader open source community. Actually, there are a lot of open source communities which are also contributing to the development of Microsoft Planetary Computer, and they are adding new and new features every day. So Hub builds on the work done by the Pangeo community to put the tools of data science to work for the Earth science community. Like Pangeo is a project, data science project. Now same thing has been extended for use by Earth science community. So APIs are built. So whatever APIs we are using in Microsoft Planetary Computer are based on the Stack community. Stack standards like spatio-temporal assets catalog to streamline and standardize the cataloging and discovery of geospatial data. So the slides which I have taken were taken from these different sources. So with this we come to the end of part 1. Now let us see how do we access the satellite data, or how do we do it in how do we do it in using a single web browser. So we'll see just by using a web browser how do we access the services of Google Earth Engine. So for accessing Google Earth Engine, first of all we need to register our Google account for access like first we need to request this, sign up for Google Earth Engine. So once you apply on the Google Earth Engine's website, so within a day or two they will approve your request. So once your account gets approved, then you can start using Google Earth Engine. Actually, Google Earth Engine offers APIs. Like there are multiple APIs. Like if you are programming in JavaScript, so then Google you can use JavaScript APIs of Google Earth Engine. Or suppose if you are a Python programmer, then you can use Python APIs of Google Earth Engine. So because we had discussed in previous lecture about Python, so I now assume that you have some familiarity with the Python. So I have taken the demonstration using Python APIs of Google Earth Engine. So first you need to sign up of the Google Earth Engine. Once you sign up to the Google Earth Engine, then they will allow you to access the Google Earth Engine cloud services. So actually now in my account I have already access to the Google Earth Engine. So as in the previous lecture, now we will be using the same Google Colab for accessing the Google Earth Engine. Otherwise, like if I search here, so if you are working in Java, if you are interested in Java APIs, then there is a code editor. So in the Google Earth Engine code editor, so you can directly write your code in the Google Earth Engine code editor and start. So then there are a lot of documentation also is available here, lot of tutorials. So there are like a lot of tutorials, everything is available, video tutorials, sample codes, so all everything is available. It's very well documented. Then you can go through the documentation and start using Google Earth Engine. So now, right now I will be using Python APIs of Google Earth Engine. So for that I am using Google Colab. So once I have created a Jupyter notebook called gedemo.ipynb. So in that I will be demonstrating you the how to use Google Colab, or sorry, Google Earth Engine. So as first is Google, what is collaboratory? Collaboratory or Colab allows us to write and execute Python with our browser, right? With zero configuration required when we are, because these Google Earth Engine APIs you can install in your local system as well. But if you don't want to install anything on your system, then directly you can go to Google Colab. So in case of Google Colab, zero configuration is required. You have free access to GPUs. Like if you want to do some deep learning on the geospatial data, then you can go. You have access to the GPUs as well. So Google Colab gives you access to the GPUs as well. Then once you have done, like you have prepared your scripts or programs, then you can share quite easily it with the other users. So basically, as we said in the previous lecture, there are two types of cell. One is called code cell and another is called text cell. So in the code cell, you write executable Python code, and in the text cell, we can write any formatted text, or we make insert images. Like with you, if you know LaTeX, with LaTeX you can write equations as well. So this is our Google Earth Engine. So for using Google Earth Engine on the Google Colab, so first thing actually you need to import a library called EE. So this EE library by default in Google Colab it comes pre-installed. So first of all we need to import the EE library. So EE, or the short acronym for Earth Engine. So first we need to import Earth Engine library. Then we need to authenticate and initialize. So first we need to run the ee.authenticate function to authenticate our access to the Google Earth Engine server, and with ee.initialize to initialize the services, right? First authenticate and initialize. So I'm calling ee.authenticate and ee.initialize. Then it asks, it gives a link, and we need to click on that link and select account. generate token. So these two permissions we need to give. Then it gives us a code. So that code we need to paste it here and run. So now it says successfully saved authorization token. Right now, suppose once it is initialized, now suppose if we want to quickly check like whether whatever we are we able to communicate to the Google Earth Engine easily. So for that, so every image on the Google Earth Engine, Google Earth Cloud or Google Cloud or Google Earth Engine Cloud is can be accessed using a container call or a construct called ee.image, and to ee.image we need to pass the actually every image or every image collection available on the Google Earth Engine will have a ID. So how do we find the ID of that image or image collection? So you can go to Google Earth Engine. So now you search for data sets. Now you can say suppose if I am interested in satellite imagery, Landsat imagery. So every Landsat image or Landsat image collection will have an ID. So we need to know this particular ID to access it on the Google Earth Engine. So like suppose Landsat 8 OLI. And suppose if I am interested in surface reflections tier 2 product. So then if I see it here, so it gives us a ID like this. Landsat / LC08 / C02 / T underscore 2. So this is the ID of the image collection. So we need this particular ID. So like whatever image we want to access, we need to get the ID of that image from the Google Earth Engine website first. Right. So here we are accessing the SRTM DEM. So DEM ee.image we are passing here which particular image ID of that image. Then we are first creating a geometry. As we said that every feature is represented as a every geometry is represented as a feature in Google Earth Engine. So e.geometry.point. So we are creating a point geometry and sampling from that DEM what is the height at that particular point. So that is called dem.sampleXY. First get elevation get info. So this is the 78.04 and 30.34 are the latitude and longitude of the IIRS where presently I am sitting. So suppose if I want to query what is the elevation at that point, so I can query it like this. If it runs properly, I can say that the initialization, so this is like the connection to the Google Earth Engine is successful. I can say now it says that elevation at IRS is 697 meters, which is closely matching with the actual height. Right. So these are the as we have discussed in the previous slide as well. So these are the different data structures of the Earth Engine. First is an image. Image is the fundamental raster data type. So any raster data type is represented as an image, IMAG in Google Earth Engine. The image collection is a stack of time series of images. Geometry is the fundamental vector data type. So any fundamental vector data type is a geometry. Then when we attach certain attributes or non-special attributes to that geometry, then it becomes a feature. So feature collection is a set of these features, and reducers are objects used to compute statistics or perform aggregation over an maybe image collection or feature collection. Then join is with the join we can combine two data sets. Then array is for multidimensional array analysis. And for mapping, we will be using a library called Folium. Folium is a leaflet's Python implementation, can be used to display our Earth image objects. So in an interactive leaflet map, Folium has no default method for handling tiles from the Earth Engine. So we need to first define a method and then add it to our. So anyway, this code is right now not important. Right now you can see that we have defined a function add EE layer. So this particular add EE layer function, what it does, it takes an Earth Engine image and displays it on the map. So whenever we are using, we will be just calling this add EE layer function. Right now it is not important to understand this. So you can actually this same function is available on the Earth Engine's website also. You can refer from there as well. Now for this particular demonstration, we will be using a data set called global GSW or global surface water data set. So GSW water data set had multiple sub data sets inside that. So one of the data set is water occurrence. So water occurrence data set is like, I think it is derived from the Landsat imagery from 1984 to 2015. I think now even 2020's data also is available. So the GSW data set contains many data layers that present the surface water data in different ways. So we will start by visualizing the visualizing the water occurrence layer, which provides a summary of where and how often surface water occurred over the entire time period between March 1984 and October 2015. So this GSW dataset has multiple bands. So whatever data we will be using is called water occurrence layer. So there are multi layers in that particular data. So first we will discuss about water occurrence layer. So in water occurrence layer, every layer what it describes. So every pixel is telling how often surface water occurred during 1984 to 205, during this entire time period. How many times water was present at that particular pixel. Maybe says, if you say the number is 0, 0 means there was, during these last 32 years, there nowhere, no time water was found at that particular pixel. So then the number is varying from 0 to 100%. So 1% means during that 32 years of time, 1% of time, this pixel was contained water. And if number is 100%, means it is a permanent water body. Like during 32 years, in all images, water was present at this particular pixel. So in this demo, we will include, like, we will see how to add a map layer for visualizing surface water occurrences. We will show how you to query the values from a map layer, add custom styling to improve the visualization, create a binary water mask. Then we will see center the mass on, like, then we will see that how do we center the uh, center the map, like sometime to our area of interest maybe. Then show, then we'll see how do we refactor the map so that it becomes more easily maintainable and readable, right? So like Landsat images, similar to Landsat image, this global surface water data set image also has an ID. So this ID you can get by from here. Like I'll search, browse by tags GSW or global surface water. So now here you can say global surface water layer 1.4. So now it is available from 1984 to, so now this is the ID of global surface water set. Now I can use this here. So I get the ID of my data set of my interest from here. And now first thing I am creating GSW e.image and occurrence. So now as we discuss, so this particular data set contains multiple layers, right? So out of that, first we will visualize the occurrence layer. So occurrence layer is telling at every pixel how frequent water was present at that pixel. Like if the number is 0%, so what does it mean? It means that during that 1984 to 20222, no time water was found at that particular pixel. So it is 1%. During that 32 or 35 years of duration, only 1% of time this pixel will contain water. If the number is 100%, that means we can say that during this entire 32 periods, every time, so almost in every image acquired during that period, this pixel contained water. So like this may be for permanent water bodies, right? So now from this image, suppose if you want to fetch some occurrence band, then we can call gsw.select occurrence. So now we have fetched them a band of our interest from the image. And now suppose, now for that, creating a map, we need to, like as you discussed, we have created a imported Folium library. So in folium.map, we need to specify location, like where the map, when we're starting, where the map will be centered. Like this is the latitude and longitude, lat long, and at zoom level, which zoom level to start, and suppose height of the map to be displayed. So folium.map creates a new map. Then we have defined a function called add EE layer. Now on this map.add EE layer, to this we are passing the occurrence object. Occurrence object contains the our data set. So now if I run it and run this stat. So here the first statement references the Earth Engine image object or GSW dataset and stores it in a variable called GSW, and second statement is fetching that single layer from the dataset into a variable called occurrence. Then third statement is adding this image to the folium map. So actually what has happened here, we have created a map, then add with add E layer, and actually we have not passed here any color palette. So because of that, no image is shown here. Now if I run it once again, just a minute, I will be just taking. So I have taken this data set 1_0. So now you can see that this particular pixels is like, if you visualize it on the map, so you can say that like these areas, so this area is showing like very bright, so this number may be 100%. Like in these pixels you can say that water was present almost every time. Now this visualization is not so good, right? Because the image is shown as grayscale. You have the portions which are very white, so it means that the occurrence of water was more, like this pixel contained water maybe 100% time. So now same thing, data set 4 is. Now let's improve the visualization. Actually here we have not passed anything. Now let's refactor our code to improve. So our script only contains 2 statements, but already we have now we have an opportunity to refactor our code so that our final script will be easier to read and maintain over time. So now first one, we have not passed any visualization parameter to this particular map. Now suppose if we pass a visualization parameter, like we want the numbers in this range and the numbers to be colored according, like next, so we will want to improve the visualization parameter, so which makes our water appear, this previous visualization making our water to appear green. Now we pass an additional argument to the add layer method, where we are passing the color palette as well, like where we want to say that wherever the when the frequency of water occurrence, like the figure is going to 100%, that color we want to display as blue, and when the number is less, like when the pixel contains water less number of times, then that we want to represent as red color, right? So we are creating a new dictionary called visualization occurrence. There we are specifying minimum value, maximum value, and color palette to be used for visualizing that particular image. So we are saying that use 2 colors. So for 0 use red, and as the number increases use blue color. Now everything is same, only thing water map that E layer, then here we are passing a second argument called visualize occurrence, and if we see the map, now you can say that, see, like if you see this particular water body, so these are the pixels which contain water almost in all the images during that last 32 or 35 years, and these images water was changing. So their water was fixed. These may be seasonal water. Like this, you can go to the any water body and visualize the data globally. Maybe you can go to the Brahmaputra region. So there you can see that, like these the pixels which are in uh, dark blue. So these pixels contain water most frequently, maybe in every image acquired during the last 32 or 35 years. Like these areas you can see. There may be some errors also in the data set. Okay. Now suppose we want to create a threshold layer. So there the number is showing like 0% to 100%. Like now suppose if you want to create a threshold, like when the pixel contains value greater than 90%, means we can say that if the pixel contained water more than 90% of time, then we can say this is a water pixel. And if it contained water less than 90% of the time, then we want to just filter out those images, right? So the water occurrence image contains information on how often water is expected using a range of values, maybe 0 to 100%. However, it may be useful to define a binary water layer. Like from this, if you want to create a binary water layer, like water and non-water pixels, based on a certain percentage of occurrences, like a threshold value. Like we can say that whenever this particular pixel contains value greater than 90, that create that as a water pixel, and if value is less than 90%, create that as. So we want to create. So how do you see how to create a binary image from that image? So we are creating a same visualization water mask. In that we are defining the color palette to be at white and black only. So non-pixels will be represented as white and pixels will water pixels as white. So first we need to mask the image. Like we are creating water mask by calling occurrence dot greater than 90. So first we are masking all the pixels which has value greater than 90. We are less than 90 we are unmasking, and we are creating a water mask. Now let's add this particular. Now instead water map dot add layer, and if we add this, now we can see it as a binary image, right? So all the water pixels now are in black. Like you can see any water body, all the water pixels are now in black color. Similarly, now suppose if we want to go to the different parts of the world, like this, if you can see anyway, you can from here you can navigate as well. But now suppose at starting itself, suppose if you want to when the map starts, you want to center it to some different area, so that you can specify from here. So here you can say this is done already. Then you can specify a location. Like suppose if you when starting your map, you want to center it around some different point. So then while creating the map, you can specify the location where to start. Like initially location was this. Now suppose if I want to map, when the map starts, I want the map to be centered at 30-degree latitude and minus 78-degree longitude. So then I can specify like this. Now if I run, the map will be centered around somewhere. So initially it was centering around Uttarakhand area in India. Now it is centered around some part of US, right? So this way you can change, you can go to any part of the world. Anyway, you can navigate from here as well. But while starting also, suppose if you want to center the map around your area of interest, then you can specify it by using the location. The second layer in our data is water occurrence change intensity. So the water occurrence change intensity data layer provides a measure of how surface water has changed between two epochs, right? 1984 to 99 and 2000 to maybe 2022. So the layer averages the change across homogeneous pairs of months taken from the two epochs. So this is showing the change intensity, like where the between two epochs where the change has increased, occurrence of change has increased, and where the occurrence of change might have decreased. So the water occurrence change intensity layer provides the measure of how surface water has changed between two epochs, like how the water frequency has changed. So for that, the name of the band is change absolute, like change equal to GSW dot select change absolute. Then we are defining a visualization parameter, then creating a map and adding that change layer to the map. Now if you see the change map, now here you can see that this is the change map of the water intensity occurrence between two epochs. So where the area is red, it means the intensity of water change has decreased, and the areas which are green, the intensity of water change has increased. This way you can visualize the intensity of water change. Then third layer available in that is water class transition. So the water transition layer captures the changes between three classes of water occurrence, maybe non-water to non-water, seasonal and permanent water, along with the two additional classes, ephemeral water or ephemeral seasonal. So the water class transition layer shows like whether this was a seasonal water or this was a some particular pixel was permanent water, or whether it's a ephemeral permanent or ephemeral seasonal water pixel. So the name of the layer is transition. So transition, I am selecting this transition layer from that, and now I'm adding the same thing. Now you can see that this is I need to add this. So the tutorial was based on the different version. I have used a different version. So change intensity, as you have seen, now you can see the change intensity in any of the area. Like suppose if you go to India, so you can see how beautifully it has captured the change intensity. Now if you go to the Brahmaputra region, here you can see that how beautifully it has captured, like the red color is showing the where the intensity of change has is been increasing during that 32 years, and the greens are showing where the intensity is red is showing where the change intensity is decreasing, and green is showing where the change intensity is increasing over the during those two epochs. Right now here same thing, like suppose if you want to see the water class transition, like how the water is changing, like whether the water is permanent. So like these are the symbologies. So you can say that wherever a blue color is there, that water is permanent water, and this is new permanent. This is the new water, has new water, like after certain years it has come, and this is like lost permanently lost water pixels. Then these are the seasonal pixels. These pixels are new seasonal. So this way you can analyze this is the summary of the water for last 42 years. Like these you can see these blue are the permanent water pixels. So if you go to the any area of Uttarakhand, so this way by reading more about this, you can see the how the surface water in the entire world is changing over the time by water occurrence, then change intensity and transition. So by analyzing this all, you can, like if you have any question regarding like how the availability of surface water in your area is changing, and then you can explore this global surface GSW data set. So this was all about today's lecture. So if you have any questions, you are welcome to post it on the chat box. I will try to answer them. So now we will see you after 5 minutes.